Hello, my name is Rylan Phipps, and today I'll be presenting my Project 3 ramjet analysis for AME431, or Intermediate Thermodynamics. Here is a brief outline of the topics that will be presented in today's presentation. Alright, so how do these ramjets work? Well, first, there are no moving parts with the exception of a fuel pump. The engine actually utilizes the speed of the aircraft to ram the air into the engine over here. Using a specialized geometry, the air is compressed, and then in the combustion chamber, a Brayton cycle takes place with combustion between the compressed air and fuel. The exhaust is then expelled into a converging diverging nozzle, in which the exhaust outside of the nozzle exit is essentially where the thrust is generated for the ramjet. There are several advantages to a ramjet, and the first one is that it produces a large amount of thrust compared to other engines in the aerospace world. They're very efficient at sonic speeds, and there are no moving parts as stated on the previous slide, so the maintenance on ramjets is actually relatively somewhat easy compared to other engines. It also has a high thrust per unit weight, which kind of goes back into this first point that was stated. Now there are disadvantages, and the main one is that it cannot be used for takeoff or landing, and therefore separate engines are needed on the aircraft, increasing the weight. As such, it's not operable in subsonic speeds. Due to the physics of the air ramming into the jet, the higher you go up in altitude, the lower the density, the lower the mass flow rate going into the engine, which equals the lower thrust. So therefore, there's a limited maximum operating altitude. Also, unstart can be a possibility. The physics of this is quite complicated and outside the scope of this presentation, but it leads to less mass flow rate entering the engine, thus leading to a decrease in thrust. Alright, so now we're going to discuss the throat to exit nozzle area ratio, and essentially it actually is what the name is. It's the area of the exit nozzle over the area of the throat of the ramjet engine, and it is governed by this equation. From one source, I found that the range for it is about 1.3326. And then in a master's thesis, in the analysis, they use 1.61. So I chose to go with 1.75 for this analysis for this presentation. Moving on to various flow conditions. For this analysis, K will be equal to 1.4. I got the area ratio to be as close as I possibly could, and also saving my sanity. So this is what we're going to use because I had some trouble with the MATLAB interface. For the first case, the back pressure and the starting pressure are going to be the same, so the pressure ratio is going to be equal to 1. And the main thing to note here is that there's no pressure differential, therefore there's no mass flow rate, so there is no velocity and no flow going through the CD nozzle. Alright, now if we decrease the back pressure a little bit, there will be a pressure differential between the start and exit pressure, and therefore there will be mass flow rate. So in this case, with this specific pressure ratio, we have a subsonic flow. Eventually, as you keep decreasing the back pressure, you'll get to a special case, and this is a special case seen right here in the graphs. And so basically we have reached Mach unity. And what happens at Mach unity is the critical pressure also occurs, and what this means is that the flow in the throat is at its maximum, which equals 1, and the flow basically kind of chokes at the throat. Continuing to decrease the back pressure, essentially what you will get is a normal shock in the diverging nozzle. The main takeaway here is there is almost an instantaneous decrease from sonic to subsonic after you cross the normal shock wave, and the pressure increases as well. As you keep decreasing the back pressure, eventually you will get the shock at the exit. And one thing to note here is still the same, that there will be a decrease from sonic to subsonic as we move across here. It doesn't show up in this graph, but down here you can see there's a jump in pressure. And decreasing the back pressure further, we will get to a point where there will be no shocks inside or outside of the nozzle, and this is what we want. This is the ideal case for a ramjet, and as such, this is called the design condition for the nozzle. We're going to briefly explore what the area ratio has the effect on Mach and pressure. So the first case is when the start is the flow choked at the throat. So decreasing, or actually increasing, you kind of see that a shock actually forms just after the throat of the nozzle. And if we decrease it, not much happens with the exception of that the flow is not choked anymore at the throat. So you can see it goes down to 1, 0.6, down to 0.5. So for the next case where the start condition is the shock at the exit, if we increase the area ratio, you can kind of see that we get kind of an overexpanded flow. And through this overexpanded flow, you kind of get like a turning angle for the flow, as you can kind of see right here. If you decrease it, this is actually the one that I found the most interesting out of all of them, is that it actually moves the shock, normal shock, upstream closer to the throat. So I kind of found that very interesting as an outcome. Alright, so now the initial stage of the design condition. So if you increase the area ratio, you get an underexpanded flow, so you kind of get a flannel expansion fan occurring right here. Also, kind of like the previous slide, you get a turning angle, as you can kind of see how it affects the flow right here. If we decrease, we get an oblique shock wave. Again, this also changes the flow characteristic and how the flow interacts, so the flow kind of has like a turning angle right here as well for decreasing the design or the area ratio. Alright, now we're going to kind of get into some actual math and using equations. So we're going to calculate P over P naught and the area ratio from mx, and mx is the velocity or the Mach right before the shock. And so from the MATLAB program, the Mach number right before the shock was found to be around 1.85356. So using this value in the following equation, we get 6.237. Now we want to find P over P naught, but we have P naught over P. So using a basic algebra, we can find this to be 0.6 or 0.16033, which matches up pretty close to what we get in the MATLAB program. Now we want to find the area ratio from mx as well, using the value found here and also all the known values. For k, we were able to find this area ratio as 1.499, which from up here you can see it is exactly the same, which is really impressive. One thing to note though is this MATLAB program probably uses the exact same equations, and so that's why we're seeing very similar numbers between the MATLAB and the actual physical mathematical analysis. Next up is calculating my, or the speed of the flow after the normal shock wave. So what we're going to do is from the MATLAB program, from the previous slide, it's the same graph with just a different value. We found it to be my of around 0.6 Mach, so about half the speed of sound. Now, we're going to do two different approaches. The first approach is using an equation and solving directly. We found mx from the previous slide, and plugging this as well as the k value, which is 1.4, we can get my squared equals 0.36 roughly, and then taking the square root of that to just get my, we get around 0.60959, which is roughly close to this value right here. Now, the second approach that we're going to take is an iterative approach using the tables, specifically table 9.3 in interpolating. So using this table over here between the values of, let's see, 1.9 and 1.8, we can interpolate to find my directly. So solving this equation, we get 0.6053, which is very similar to what we found numerically through the equation, and this matches up pretty almost exact with what was produced from the MATLAB analysis or simulation, if you will. Alright, so the last thing for this presentation is we're going to try to find how we can find a py over px ratio from the p over p naught ratio. And now, as you can see, the py over the px ratio is essentially how much the ratio is changing before and after the shock. And so there's a couple of ways that we can approach this. So the first approach is through an equation directly. From the previous two slides, we found the Mach before the shock and the Mach after the shock. And K throughout this whole entire presentation has been 1.4. So plugging in those numbers, we found it to be around 3.85. So now from the MATLAB plots, the mx values and my values were taken above the MATLAB plot for Mach versus location. That's just one thing to note of where these numbers came from. Now using the P over PC MATLAB plot, which is right here, we took the value of Px over P naught x, which is the pressure before, and then we took the Py over P naught y, which is the pressure ratio of after, as you can see right here. Now, in order to find Py over Px, we can just take these two ratios and divide them. Through algebra, the P naught y and the P naught x's kind of cancel out, and therefore it leads us to this answer right here, which is 3.84. And this is roughly exactly the same as this right here. So these are two ways that you can find the ratios. Alright, so in summary and conclusion of this presentation, now you know exactly how ramjets work, the advantages and disadvantages of the ramjets. You also know the various flow conditions dependent on the back pressure and the starting pressure. We've also know how the area ratio affects flow conditions from expansion fans and moving the flow, moving the normal shock upstream into the nozzle. And you've also gained some insight into the governing equations of the MATLAB simulations. Thank you very much for watching this presentation.